Okay, so in this video I'm going to have a look at the 2015 Higher Level Maths Paper 1, question 8. This question here is about an oil spill that occurs offshore in an area of calm water with no currents. The oil is spilling at a rate of 4 by 10 to the power of 6 cubic centimeters per minute. The oil floats on top of the water. So the first thing we've got to do is complete this table, and it shows the total volume of oil on the water after each of the first 6 minutes of the oil spill. Well, we were told here that the oil is spilling at a rate of 4 by 10 to the power of 6 centimeters cubed per minute. So in the first minute here, we're going to have 4 centimeters, cubic centimeters, 4 by 10 to the power of 6. Well, we're told here that these numbers here are by 10 to the power of 6 cubic centimeters anyway. So what we're going to do here is start with 4. After 2 minutes, the rate is going to be 8 by 10 to the power of 6 centimeters cubed per minute. After 3 minutes, it's going to be 12. After 4 minutes, it's going to be 16. After 5, it's going to be 20. After 6 minutes, it's going to be 24 by 10 to the power of 6 centimeters cubed per minute. So that's part A done. Okay, so next part then we've got to look at is part 2 here. I have that down twice here, but it's just a case of drawing a graph to show that the total volume of oil on the water over the first 6 minutes. So we've got to draw a graph of this table here basically. So let's just put in the numbers. Well, after 1 minute, we're looking at 4 by 10 to the power of 6. So 1 is going to be 4 here. 2 is going to be 8. So 2 is going to be 8 here. 3 is going to be 12, so 3 is going to be 12 here. 4 is going to be 16. You can see it's going to be a linear graph. So 5 is going to be 20, so we're going to end up here. And finally 6 then is going to be 24 by 10 to the power of 6. So we've just got to join these up now. So it's going to go through 0. I'm going to start down here, and we're just going to draw a line through these points. And that's it. That's our graph. Okay, so that's all we had to do in that one. That was the second part. So the third part then is write an equation for V, the volume of oil on the water in centimeters cubed after t minutes. So we're going to look at the volume after t minutes. Okay, so the volume after t minutes, we write it down as V of t, is just going to be 4 by 10 to the power of 6, which is what we were given up here. That's the rate at which the oil is spilling per minute, 4 by 10 to the power of 6. So our volume then, after t minutes is going to be 4 by 10 to the power of 6. Remember, this is what occurs every minute. So it's going to, we just have to multiply that by t. So this is our formula for the volume of oil on the water in centimeters cubed after t minutes. Okay, so part B then. The spilled oil forms a circular oil slick 1 millimeter thick. Write an equation for the volume of oil in the slick in centimeters cubed when the radius is 4 centimeters cubed. Okay, so what we're really looking at here is a cylinder. So what we're going to do here is just look at the volume of a cylinder. The volume of a cylinder is going to be pi r squared h. So in our particular case, we've got pi times r squared times the height in this particular case, which is 0.1. It's 0.1 because 1 millimeter is equal to 0.1 of a centimeter, or 1 centimeter is 10 millimeters. So I've just converted to centimeters here. Okay, so our solution here is just put the 0.1 first, and that's pi r squared, and that's centimeters cubed. That would be our volume when the radius is r. Okay, so part 2 would be then is, let's see, find the rate in centimeters per minute at which the radius of the oil slick is increasing. The radius is 50 meters. So we've got to find the rate in centimeters per minute at which the radius of the oil slick is increasing, the radius of the oil slick. So what we really want here is dr dt, the rate at which the radius here is increasing with respect to time. So we need the dr up here, we need the dt down here, and then we need something else here and here. So what I'm going to put there, I'm going to look at volume. Because we've done something up here with volume, I'm going to put dv here and dv here. So let's do that. So put dv here and dv here, and I'm going to work these two out, multiply them, and that'll give me dr dt. So the first thing we want is dr dv. Well, from our formula that we made up here, we have volume. Here, volume is equal to 0.1 pi r squared. So if I write that down here, volume is equal to 0.1 pi r squared. So what I can do here is find VDR. I can differentiate V with respect to R. So the R we can see is here. So I'm differentiating V with respect to this variable here, R. So if I do that, I'll get, well, all you got to do here is just bring the 2 down. So I'm going to bring the 2 down, multiply it by the 0.1. The pi will remain there. Remember, pi is just a constant. It's 3.14 and so on. The r is the variable, and we've got to reduce the power by 1. So that's r to the power of 1 here. So what I end up here with is 0.2 pi r. 0.2 pi r. That's dv dr. So that just means then that dr dv, I've inverted this fraction here, so I'm just going to invert this over here as well. Remember, this is over 1, so I can just invert it as well. 0.2 pi r is on the bottom here. So now I have my dr dv. What I need as well is the dv dt. But if we go back to the start again, we'll see that dv dt was given in the original question here. The oil is spilling at a rate of 4 by 10 to the power of 6 cubic centimeters per minute. So in other words, that's dv. That's how the volume is changing with respect to t, dv dt. So that's equal to 4 by 10 to the power of 6 cubic centimeters per minute. So that's dv dt. So we have everything we need then. So I'm just going to put that into my formula here. So if I come back up here, dr dt is dr dv, which is what I've calculated down here, 1 over 0.2 pi r. Got to multiply that by vdt, which is 4 by 10 to the power of 6. And remember, that's over 1 if you like. So if you do that, you just get 4 by 10 to the power of 6 over 0.2 pi r. So this is my dr dt. This is how fast the radius is changing, how fast the radius is changing. And this would be, by the way, centimeters per minute. Centimeters per minute. Let me just separate these out here. Okay, so we were asked in the question then to look at that particular rate, the rate at which the radius is changing with respect to time when the radius is 50 meters. So in other words, we've got to substitute 50 meters in here for r. Now remember, we're talking about centimeters here, so we've got to change that 50 meters to centimeters. There are 100 centimeters in a meter, so our dr dt then, so at r is equal to 5,000 centimeters. So this is what we're looking at now. Dr dt is going to be equal to 4 by 10 to the power of 6 divided by 0.2 times pi times 5,000. And when you calculate that, you get 1273.3. 1273.3, and that's going to be centimeters per minute. That's our answer there. Okay, so in part C, we've got to show that the area of water covered by the oil slick is increasing at a constant rate. So really what we're looking for here is dA dt, the rate at which the area is increasing with respect to time, the rate at which the area is increasing. So we want dA dt. So we're going to put the dA up here, we put the dt down here, and the other variable that we're dealing with here is the radius. So I'm going to put dr here and dr here. So these will cancel if you like, and we just end up with dA dt. So the first thing I'm going to do is work out dA dr. We know that the area of our oil spill is going to be the area of a circle. So it's going to be pi r squared. So that just means dA dr. So we're going to differentiate area with respect to radius here. That's just going to be 2 pi r. 2 pi r. So all we're doing here is taking the 2, bring it down in front, multiplying it by the pi, write down the r, and reduce the power by 1. So now I have my dA dr. Next thing I need is dr dt. Okay, so what we're going to do is use this dr dt here. What we're going to do is use this expression here for dr dt. So let's write all that down. We have both of these now. Okay, so our dA dr is 2 pi r. That's over 1. We want to multiply that by what we got earlier, and that's 4 by 10 to the power of 6 over 0.2 pi r. Now if you look at that, you can see here that there's a pi times r here on the bottom, and there's a pi times r on the top here. So and they're all multiplied on the top, multiplied on the bottom, so we can just cancel these if you like, or divide that pi r into that pi r, and we'll get 1. So what we're actually left with here is 2 times 4 times 10 to the power of 6 all over 0.2. And if you work that out, you get 4 by 10 to the power of 7. 4 by 10 to the power of 7, and that's square centimeters, centimeters squared per minute. And you can see that is a constant. There are no variables in here. So we've ended up with a constant here. So that means, that's what we were asked to do, I think, wasn't it? Show that the area of water covered by the oil slick is increasing at a constant rate. So it's increasing at a rate of 4 by 10 to the power of 7 square centimeters per minute. Okay, so part D then, last part here, we have the nearest land is 1 kilometer from the point at which the oil spill began. Find how long it will take for the oil slick to reach land. Give your answer correct to the nearest hour. The nearest land is 1 kilometer away. So that's we've got to change that into centimeters because we're dealing in centimeters. So 1 kilometer is 1,000 meters, and that's going to be 1,000 multiplied by 100 centimeters. So that's just going to be 10 to the power of 1, 2, 3, 4, 5. 10 to the power of 5 centimeters is 1 kilometer there, okay? So we know that the area of our final circle, area of a circle is pi r squared. Now we want our radius. When our circle reaches land, radius will be 10 to the power of 5 centimeters. So in other words, our area is going to be pi by 10 to the power of 5 squared centimeters. This is our pi r squared, which is pi times 10 to the power of 10 centimeters. Squared, that should be squared here. So our area, once the oil slick reaches land, the area of the oil slick will be pi times 10 to the power of 10 centimeters squared. So how long does it actually take? Well, we know that the area of our oil slick is increasing at a constant rate. We work that out up here. So it's increasing at a rate of 4 by 10 to the power of 7 square centimeters every minute. We want our circle to reach pi times 10 to the power of 10 square centimeters. So all we've got to do is divide this by this, and that'll give us the time it takes to reach land. So our time then is just going to be pi times 10 to the power of 10 divided by 4 by 10 to the power of 7. So that's just going to give us, well, we've got pi over 4 here, and the 10 to the power of 10 divided by 10 to the power of 7 is just going to be 10 to the power of 3. Subtract the powers, and so when you work that out, you get 785.398. And remember, we're talking about minutes here all the time. We've converted everything to minutes. So give your answer correct to the nearest hour. So to the nearest hour, well, all you've got to do here is just divide that by 60. So you take 785.398 minutes, divide that by 60, you get 13.09, which to the nearest hour is going to be 13 hours to the nearest hour. And that's it for this particular question.